Armstrong Medical is the manufacturer and patent holder of Amsorb Plus, an absorbent for anesthesia, recognized as the safe alternative to conventional soda limes and barrelime. Amsorb Plus is available worldwide and enjoys the patronage of major healthcare institutions as it increasingly becomes the absorbent of choice. Absorbent is necessary within an anesthetic breathing circuit during low-flow anesthesia to absorb and neutralize endogenous carbon dioxide produced during respiration. Expired gases are then rebreathed by the patient. Known as low-flow or circle system anesthesia, its main attraction is reduced consumption of vaporous anesthetic agents that are dosed into the system as a percentage of fresh gas flow and are an expensive commodity. The absorbent isn't replaced until exhaustion is indicated by capnography, typically when inspired carbon dioxide exceeds 0.5% of the inhaled gas volume. The absorbent's only role is to absorb carbon dioxide. It should be compatible with the anesthetic vapor and under no circumstances interact with the vapor to produce chemical degradants. Other than Amsorb Plus, commercially available absorbents are mostly sodium hydroxide based, known as soda limes. It's these absorbents that are commonly associated with breakdown of the anesthetic vapor and patient safety issues. Development of low-flow anesthesia has been complicated by poor absorbent performance and the necessity for extensive patient monitoring. The inability of absorbents to ensure safety has impacted on the perception of low-flow anesthesia as a viable and safe technique. The unpredictable behavior of soda limes and barrelime, as well as the widespread reporting of clinical incidents associated with their use, has led to uncertainty. Not knowing when absorbents are desiccated and hence potentially dangerous has led many physicians to look for alternatives. Some absorbents are known to degrade anesthetic vapor into potentially toxic compounds, of which carbon monoxide, methanol, formaldehyde, dimethoxymethane and compound A have been reported, along with related adsorption or disappearance of anesthetic vapor into desiccated absorbent. Carbon monoxide is an innocuous toxin, a silent killer with an affinity for hemoglobin greater than oxygen. A long half-life makes it resistant to displacement from hemoglobin. Formaldehyde is more obvious. It's a potent respiratory irritant and carcinogen. These degradants have no role to play in anesthesia other than posing risk to patients. Amsorb Plus has been developed to eliminate these problems. Amsorb and its second-generation product, Amsorb Plus, were developed in 1997 and 2002 respectively, in collaboration with the Queen's University Belfast. A proliferation of clinical reports and near-death incidents with conventional absorbents prompted the inventors to reformulate an absorbent without the strong chemical base of soda limes, which were known to cause destruction of the anesthetic vapor to carbon monoxide. Amsorb Plus became the solution to a real clinical problem. It's incapable of degradation of anesthetic agents in any state of use. It simply absorbs carbon dioxide. Over 170 papers have been published on the performance of absorbents in the presence of anesthetic vapor. Many discuss the unpredictable nature of absorbents and their ability to produce toxic levels of carbon monoxide. Previously, nothing was known about the ability of absorbents to degrade sevoflurane. The Cannizzaro reaction characterized the transhalogenation of sevoflurane to compound A and compounds B to F, while in the presence of fresh or desiccated soda limes. Compound A has been shown to be nephro- and hepatotoxic in rats. Production of carbon monoxide from exposure of isoflurane, N-fluorane and desflurane to desiccated absorbent was first described amid suggestions that, such was the seriousness of the problem, the anesthetic agents should change rather than the formulation of the absorbent. ECRI, the safety organization, issued hazard alerts on the use of absorbents, and many eminent authors discussed measures to limit the danger to patients. But it wasn't until Murray first described Amsorb in 1999 that users had a viable alternative to soda limes and barrelime. In the same journal, Professor Dr. Evan Karash described the invention as elegant in its simplicity. More ECRI warnings followed, along with clinical reports supporting the use of Amsorb. Regrettably, serious clinical incidents continued, some involving combustion of absorber canisters, in which sevoflurane is thought to have reacted with desiccated absorbent, producing carbon monoxide, methanol, formaldehyde, and heat, preceding explosion and fire in the absorber. In conjunction with an alert issued by FDA MedWatch Safety Information and Adverse Event Reporting Program, Abbott Laboratories, the manufacturers of ultane sevoflurane, reported in a letter in November 2003 that clinical adverse incidents are possible, in which sevoflurane could react with absorbents, creating extreme heat, carbon monoxide, methanol, and formaldehyde. An earlier study by Holak at the University of California warned of the potential for this occurrence and demonstrated the conditions under which the absorber canister, gas, and related apparatus would self-combust. Finally, the APSF, Anesthesia Patient Safety Foundation, convened a conference of invited medical experts and absorbent manufacturers in which a consensus statement was reached, suggesting that absorbents that significantly degrade anesthetic agents should not be used. Amsorb Plus does not contain strong base chemicals common to other absorbents. Instead, the absorption accelerant is calcium chloride. Consequently, Amsorb Plus is completely inert in the presence of anesthetic agents. Its color indicator responds to desiccation without requiring the presence of carbon dioxide. Granule diameter and length are constant, and special production controls limit the presence of dust. Simulated clinical testing is used to qualify each production lot prior to release. The product is available in a variety of loose-fill packages and pre-packed canisters. Unlike soda limes, Amsorb Plus is not caustic and can be handled and disposed without special precautions. Amsorb Plus is clinically proven to prevent degradation of inhalational anesthetic agents to carbon monoxide, methanol, formaldehyde, dimethoxymethane or compound A, and to have minimal adsorption or disappearance of the anesthetic vapor into desiccated absorbent material. Amsorb Plus has a gradual and permanent color change to indicate loss of absorption capacity and the extent to which it has become dehydrated. The color change mechanism of Amsorb Plus is triggered by dehydration of the material, either from the drying effects of gas flow or from carbon dioxide absorption. It's therefore important to switch off gas flow during periods of non-use to optimize the absorption capacity of Amsorb Plus. The circumstances under which soda limes and barrelime become desiccated are well documented, but general opinion that careful management of these absorbents will avoid degradation of the anesthetic agent may be somewhat misguided. To avoid such outcomes, these absorbents are required to remain hydrated during clinical use. However, the chemical reaction that allows the absorbent to absorb carbon dioxide forces moisture from the material, exponentially increasing alkalinity, potentially enabling the absorbent to produce carbon monoxide while simultaneously absorbing carbon dioxide. Clinical reports confirm that anesthetic agents are capable of breaking down in the presence of desiccated soda limes and barrelime to produce carbon monoxide. In the production of formaldehyde, we know of no reliable measurement tool or technique to alert the user to its presence during anesthesia. The instability of formaldehyde makes it difficult to measure even in vitro, yet it should be noted that it can be produced in vivo at levels that exceed maximum exposure limits. Bedi found over 8 parts per million formaldehyde with desiccated soda lime, which compares to the National Institute for Occupational Safety and Health's occupational exposure guidelines of 1 part per million for a 30-minute period. Bedi reported that formaldehyde is a potent respiratory tract irritant and carcinogen, and has been shown to cause post-operative nausea and vomiting. If other absorbents do not change color on desiccation, how do you know they're safe for use? We asked a leading expert in this field.
Well, all carbon dioxide absorbents contain a simple pH indicator. In the fresh state, the material is predominantly alkaline. Now, during the process of carbon dioxide absorption, this pH changes to become less alkaline or even slightly acidic due to the formation of carbonic acid. Furthermore, in traditional absorbents, sodium carbonate is also produced. Now, if these absorbents are allowed to stand idle for a short period of time, the sodium carbonate is reformed back to sodium hydroxide, thus changing the color again and giving a false impression as to the hydrated state. Because Amsorb Plus contains no strong alkali, it will retain its exhausted color change. As a practicing clinician, particularly interested in patient safety, I see no reason for the continued use of carbon dioxide absorbents that contain strong alkali.
The color indicator in soda limes and Amsorb Plus is pH sensitive. In Amsorb Plus, it responds to the dehydrating effects of an exothermic reaction during carbon dioxide absorption or from contact with anhydrous gases such as oxygen. Even ambient air will dehydrate Amsorb Plus and trigger the appearance of color. However, in the case of soda limes, the color reverts to its fresh color when contact with carbon dioxide ceases, often after only a few hours of non-use. Desiccation of soda lime through contact with anhydrous gas or moisture loss through exposure to ambient air does not trigger the color indicator. Soda lime can be desiccated but appears fresh and safe for clinical use. Laboratory experiments show that 1 kilogram of desiccated soda lime absorbs a clinical loading of 200 milliliters per minute carbon dioxide for 1 hour to break through to 0.5% volume, with simultaneous production of carbon monoxide and adsorption or disappearance of the anesthetic vapor, presumably into the desiccated material. It's widely accepted that desiccated soda lime is capable of degradation of anesthetic vapor to carbon monoxide and other toxic degradants. Under certain circumstances, carbon monoxide in high concentrations is possible and could go unchecked unless co-oximetry is used. In vitro work by Kaitzer reported peak carbon monoxide levels of 13,000 parts per million and highlighted Henderson and Haggard's index of toxic effect of carbon monoxide, in which a 1-hour exposure to more than 1,500 parts per million carbon monoxide is deemed dangerous to life. In a phenomenon known as adsorption, desiccated soda lime and new generation absorbents containing molecular sieve zeolites or silica entrap anesthetic vapor as well as carbon dioxide. Nolle reported a loss, or adsorption, in a desiccated molecular sieve containing absorbent of 89% of the inflow of 0.5% isoflurane for over 60 minutes, in combination with production of carbon monoxide. Adsorption is characterized by condensing and accumulation of the vaporized agent on the absorbent granules, and revaporization of the agent when canister temperature rises during carbon dioxide absorption. There's potential for reduced depth of anesthesia from agent adsorption when using these absorbents. It's thought to be greater at low fresh gas flow rates and when soda limes, barrelime and absorbents containing zeolites or silica are used. Clinical signs of adsorption may include inspired concentrations of the anesthetic agent being markedly different to that of the vaporizer setting. Recollection by the patient of the surgical event or pain during surgery is possible, given inadequate anesthetic delivery. The concomitant use of muscle relaxant drugs could mask a patient's response to surgical stimuli, allowing patient awareness to go unchecked. During routine anesthesia, the source of patient awareness would rarely be attributed to a malfunction of the absorber canister, but this source should be checked if soda lime or molecular sieve or silica-containing absorbents are in use. The modest cost increase from using more absorbent during low fresh gas flow rates is a fraction of the savings made from reduced anesthetic agent consumption. As an example, the decrease in the cost of using sevoflurane during low flow is exponentially greater than the increased consumption of absorbent. Many users dispose of soda lime before exhaustion in order to avoid using desiccated material. Cobos, in an audit of discarded soda lime, found that material had a remaining absorption capacity between 13.5 and 73.3%, with a mean of 44.8%. This is an expensive practice, which is not required with Amsorb Plus. Some anesthetic machine absorbers allow reverse or retrograde gas flow, which will desiccate the absorbent. Absorbents such as soda limes that have a reversible color change during carbon dioxide absorption won't change color during this type of desiccation. Consequently, they appear fresh and indicate nothing of their lack of hydration. The most desiccated portion of the absorber canister is then in immediate contact with the vaporous anesthetic during subsequent clinical use. The existence of retrograde flow is best illustrated by using Amsorb Plus, which will show coloration from desiccation through retrograde flow or carbon dioxide absorption. Amsorb Plus is available as loose fill material in bags, jerry cans or in pre-filled disposable absorber canisters. The can pre-filled canister is designed for use on GE Healthcare anesthesia workstations in the upright or inverted position, while the bubble can pre-filled canister is designed for use on Draeger medical workstations. With their ergonomic design, integral water trap and high absorption performance, managing the low-flow anesthesia circuit is simple. Fitting to jumbo absorber canisters, this conveniently packaged 1 kg pre-filled cartridge offers excellent flow dynamics to assist absorption. 1 and 1.5 kg bags and a 5-litre jerry can contain loose granules ready for filling absorber canisters. Care is advised when filling. As low-flow anesthesia with Amsorb Plus becomes an established technique, we'll develop pre-packed canisters to suit new anesthesia machines and to ensure that wherever low-flow anesthesia is practiced, Amsorb Plus is the absorbent of choice. Amsorb Plus is unique, an original and first-to-market product developed through clinical research. There's sufficient evidence-based research to discourage the continued use of absorbents that contain sodium, potassium and barium hydroxides, zeolites or silica. Amsorb Plus can be used until exhaustion, as indicated by capnometry, without fear of anesthetic degradation and with the added benefit of a gradual and permanent color change in line with progressive dehydration of the material. The economic use of absorbents is also important, albeit to a lesser extent than patient safety. Discarding absorbents before they've become exhausted significantly increases their utilization cost. Hospitals would benefit greatly from a significant decrease in anesthetic vapor costs should they choose to use lower fresh gas flows during the maintenance phase of inhalational anesthesia. The APSF recommends that a safe absorbent be used during low-flow anesthesia. Amsorb Plus is that product.